Stanford University.
Okay, let's come to some observational facts, or connections between observational facts and the equations. It's impossible to really give any kind of justice to the observational facts without putting them into a context of the fundamental cosmological equations. So let's begin with them. We've already begun with them, but let's begin with them again and define some observational quantities, quantities which astronomers can and do observe. All right, the basic equation, as always, at least for a homogeneous universe, is the Friedmann equation, A dot over A squared. And that we can also give another name. We can call it the Hubble constant squared, or the Hubble, somebody suggested that we call it the Hubble function since it depends on time, and that's fine. You can call it the Hubble function. And I suppose you could call its value today, at the present time, I suppose you could call it the Hubble constant, keeping in mind that it's not a constant. But when people quote, the Hubble constant is so many kilometers per second per megaparsec, or whatever it is, they're quoting the value of the Hubble function today. I'll just call it, if I call it the Hubble constant, and just forgive me, I simply mean A dot over A. This is the Hubble constant squared, and as we know, that is equal to good old 8 pi g over 3 times the energy density minus a term for, and the usual energy density, minus a term coming from curvature, and that curvature term has a k in front of it. K is either plus or minus 1 or 0. It's never anything but plus or minus 1 or 0. Positive for a spherical geometry, negative for the hyperbolic geometry, and 0 for the flat geometry, divided by a squared. The role of A is to go into the metric. Over here I'll write the metric. Well, I think we need a little more room for it. I'll write the metric. The connection between A and the metric is that the metric ds squared is equal to minus dt squared plus the radius at time t squared. And now I'm going to use what do we have here? We have a bracket, dr squared, and then what goes in addition? An angular piece. And the angular piece is one of three possibilities, depending on k. The first one would be flat space. Let's take the case of flat space. That's k equals 0. Then this would be r squared d omega 2 squared, the 2 sphere of the sky. What about k equals plus 1? What do we put there? Anybody remember? Sine of r squared. So this could be sine of r squared, or if it's negatively curved, hyperbolic sine of squared. All right, so let's give it, instead of writing 3 separate equations, let's just call it c squared of r, where c has the following meaning. C is equal to sine of r when k is equal to plus 1. C is equal to hyperbolic sine of r when k is equal to minus 1, and c is equal to r when k is equal to 0. That makes one simple formula, and we just have to remember which one we're using. 3 different spatial geometries and an equation of motion for A. And that's our basic, okay. All right, now, the energy density can come from various sources. The actual only sources that we really know in the current universe are of three kinds. There are three contributions to rho, and rho appears, as far as we can tell, to have only three main important contributions. The first is radiation, and radiation energy density is some constant representing the amount, the number of photons per unit volume, or the number of units of energy per unit volume today, divided by a to the fourth. Then there's another contribution associated with ordinary particles, non-relativistic particles. We usually call that matter, and that's divided by a cubed. Then there's the possibility of vacuum energy. Let's actually put here 8 pi g over 3 and continue to use the right-hand side the way I've written it. Then the vacuum energy would be times lambda, the cosmological constant. That does not dilute with increasing radius. That's it. But let's add in to rho, let's add in minus k over a squared, minus k over a squared, plus this. In other words, let's include this over here as part of rho, and then we will put in here minus k over a squared. I'm not sure why I did that. Why did I? Well, yeah, it's okay. We can do it. Yeah. Okay. That's this. And what is this equal to? It's equal to h squared. It's equal to h squared. Now think about this equation today, at the present time. This says that a certain set of 4 quantities has to add up to h squared. That's a constraint, that a certain set of 4 quantities has to add up to h squared. And we can ask, how much today, present, in the present universe, how much of adding up to the right-hand side comes from radiation, how much comes from matter, how much comes from dark energy, lambda, and how much is left over in this curvature term? That's a reasonable question. The scale factor today is some number. We're going to talk about it in a little while, how big it is, but it's some number, and each one of these terms has some value, and h has some value. How do we measure these terms? Let's think about how we measure them for the moment, or how we might measure them if we could. H is the Hubble constant. Hubble measured the Hubble constant. What he did was he measured the relation between velocities as determined from redshifts. I'll come back to redshifts in a little while. He determined velocities as a function of distance. How do you get distance? You get velocities from redshift. How do you get distance? Luminosity, brightness. A distant bulb looks dimmer than a close bulb. So it was basically redshift versus luminosity that he plotted. Okay, and he measured the Hubble constant. The fact that he mismeasured it by a factor of 10, that was not the important thing. And that's true. He did mismeasure it by a factor of 10. But in principle, with better measurements. And these were not cosmological measurements, incidentally. By cosmological, I mean measurements taking place on a scale of tens of billions of light years. These were measurements of our local properties of a few clusters of galaxies. And so they did not penetrate back deep into the past. For his purposes, since they weren't penetrating back and deep into the past, the Hubble constant was a constant. He wasn't looking at it at different times. He was looking at it now. Well, slightly not quite now, but not too bad. So, yeah.
So this is an astronomy question, I guess, but how did he know these things all have the same brightness? seems like there's a kind of catch-22 or something there.
Yeah. There's the whole story of the cosmic distance ladder and how, and it's a story of many different little pieces, overlapping. You know, how do you measure the distance to the nearest stars? You do it by parallax. And then you find certain stars that always behave in a particular kind of way, called Cepheid Variables. They behave in a certain very definite way, and they have a very, very definite relation between their period and their luminosity. And that you determine from stars which are close enough that you can get the distance to them from parallax.
So those were probably in the Milky Way.
Those were in the Milky Way. For sure they were in the Milky Way. And that gave you a candle, a standard candle to work with, the Cepheid variables. You could then apply it to more distant things. And you worked your way up a ladder. Supernova are the best standard candles. And we're going to talk about that. We're going to talk about that. And of course, velocity he measured by redshift. Velocity by redshift and distance by a sequence of overlapping standards that were around.
Just double checking, are C sub r and C sub m absolute constant independent of time?
Yeah, they're constants independent of time. Radiation scales like 1 over 8 to the 4th. Matter scales or dilutes like 1 over 8 cubed. Vacuum energy doesn't dilute. And the curvature term, which you can think of as a kind of energy, if you like, an energy of curvature, scales like 1 over a squared. Okay, so Hubble measured h. We do a better job of measuring h, but basically you measure h by measuring the relationship between distance and velocity or redshift and luminosity. But you want to do it, you don't need to go to very huge distances to do so. And therefore, you're not looking back deep into the past, and you don't have to worry too much about h varying. So Hubble measured this. Now, what about C radiation? Well, we can actually look at the amount of radiation in the universe. Most of it is in the form of the cosmic microwave background, which we will come to, but it's very feeble. There isn't much energy there in the form of photons. It's a tiny fraction of the other kinds of energies, and that we know just by measuring the photons that exist around us, the black body photons, the ordinary photons, and again, there's nothing terribly cosmological about the measurement. You don't have to go very deep into the distant past, nor do you have to go very far away. You have to have a big enough volume to average over, but we pretty much know that radiation is today inessential, not very important. Okay, that's not there. Matter, well, what do we know about matter? We look at the galaxies, we see how much hydrogen is in them, we see how much luminosity is coming out of them. We make studies of stars. We know a good deal about average stars. And from the average properties of stars and interstellar gas and things which are technical but not conceptually terribly difficult, we measure all the matter that we can see, the luminous matter, the matter that can be seen. We add it all up. And we have a pretty good idea. As the years go on, we measure better and better how much luminous matter is out there. The luminous matter is presumably all in the form of atoms and protons and nuclei and electrons. And we get an estimate of this number here. That number today, the density of energy in the universe today on the average is about 1 proton per cubic meter. So it's very low, but much higher than the radiation energy density. So 1 proton per cubic meter is this term. For the moment, let's forget about vacuum energy. Well, we'll come back to it. And let's ignore it for a moment. Yeah.
What about the dark matter? Would that
Yes.
one
We're going to
cease
come
again?
to that. We're going to come to that. I'm being slightly hysterical. Slightly historical. Yeah. I want to do this with a bit of history in mind. This is as it was when I was a young physicist, let's say. C radiation, negligible. C matter, substantial, big deal, 1 proton per cubic meter. Nobody believed there was a lambda, so we forgot lambda. And then H had been measured. All right. Incidentally, the relative ratios of these today, the ratios depend on time because they scale differently, but the ratios today are called omega. So this would, not the values of these, but the ratios. The ratios are omega R, omega M, omega lambda, plus omega curvature. Omega curvature may be negative. And the rule is these must add up to 1 for the simple reason that their definition is just the magnitude of them today divided by h squared today. In other words, the omegas are the fraction of h squared today contained in each one of these terms. All right, so as I said, as a young physicist, everybody thought that omega r was equal to essentially 0, which it is. Omega matter was what you measure when you look out and look at the light coming in, the stars, the interstellar matter, and so forth, roughly 1 proton per cubic meter. Omega lambda, nobody ever heard of it, didn't believe it existed. Einstein had told us it didn't exist, and so we then had a situation where we could compute and know what omega k was. Or in other words, going back to this equation over here, this term was negligible. This term was believed not to be negligible. This was unknown. And h had been measured. H had been measured at about a factor of roughly 20 or maybe 30 times this over here. H had been measured pretty well, and it was too big to correspond to cm over a cubed. In other words, of this 1 here, this had not been discovered. This was negligible. The omega matter was something like 1 over 20, maybe 1 over 30. I'm not sure exactly how big. Roughly 1 over 30. This was small. And the only conclusion was that omega k was almost equal to 1. Almost equal to 1 meant that k over a squared, or minus k over a squared, had to be close to h squared. So let's write that down. K, well, we can say what the sign of k is immediately, right? The sign of k has to be negative. That was the first conclusion. The sign of k is negative. Open, infinite universe, it looked like. K was negative, and 1 over a squared equal to Hubble's measurement of h squared. Now, why? Because this just appeared to be too small. Too small to make up h squared. The only thing around that was big enough was this. And that in turn told us, or we thought it told us, how big A is in terms of h. Now, h has another meaning, at least within the context of matter-dominated universe. Let's go back to the matter-dominated universe, which after all, this is what we have here, and write down the equation for A. If you remember, A in the matter-dominated universe goes like T to the 2/3. For most of the history of the universe, in fact, this term is not as important as the matter term. 1 over a squared for small a, when the universe was small, was smaller than this term here. At late times, it's true, this one got bigger. But at early times, for most of the history of the universe, even though the matter was pretty small, it was still true that this term, for most of time, competed favorably with this term. So this was pretty good. This was a pretty good approximation. It fails at late time, but it's pretty good at early time. And so let's calculate a dot over a dot over a. What's a dot? A dot is the time derivative of t, t to the 2/3, which is 2/3, t to the minus 1/3, and then we divide it by a. So we divide it by another t to the minus 2/3. Altogether, a dot over a is just 2 over 3t. So the Hubble constant, in fact, we know how the Hubble constant varies with time. In this model, in the model of a matter-dominated universe, the Hubble constant, we can write this now, the Hubble constant, another way to write the Hubble constant, is it's just 2 divided by 3t, and of course it's not a constant. But we can ask, what is it today? This equation was being applied today, so what is it today? The Hubble constant today is just equal, let's call it h today, is just equal to 2/3 the time today. What does the time today mean? It means the age of the universe. Let's call it capital T. Capital T stands for the age of the universe. In other words, how long it was since the universe was very small. We don't know exactly how small, but how long since the scale factor was many orders of magnitude smaller than it is today. That's what h is. It's essentially 1 over the age of the universe, or to be more exact, it would be 2/3 over the age of the universe.
What are the units of t?
Time.
No,
Seconds.
seconds?
Sure.
No, but it's just 2/3, 1 over t. I mean, there must be some speed of light.
No. No. The units of the Hubble constant are 1 over time.
But I mean, time can be years, hours, seconds. That's what I'm asking. Which time unit is this?
Which units would you like to use? Which units would you like to use? Seconds? Years. Answer's about 1 over 10 to the 10th.
Doesn't it just depend on what h is? I mean, you can define h in whatever units you want.
That's right. And whatever units you define the age in, those are the units of h. If you define it in terms of...
I just realized it has units of time also.
Yeah, look, what is the Hubble constant? It's a relation between velocity and distance. What is the connection between velocity and distance? Time. So the Hubble constant, even though people, if you go and you look in Wikipedia or something for the Hubble constant, they will quote it as something like 80 kilometers per second per kiloparsec per something. I don't remember. But that's an astronomer's unit. The astronomers use the unit because it's good for telescopes. But from our theoretical point of view, the Hubble constant is just 1 over the age of the universe, at least for the matter-dominated. Incidentally, if it was, let's suppose it was radiation-dominated. If it were radiation-dominated, in other words, if there was no matter, only radiation, this would be t to the 1/2, and h today would be 1 over 2t. So whatever kind of nice equation of state you have, for most equations of state, the Hubble constant today is related to the inverse age of the universe. Okay. That's good. Okay, so we know something else from the Hubble constant. Having measured it, Hubble knew, as I said, he was wrong by a factor of 10. Got the Hubble constant too large, if I remember, and therefore the universe was too young by a factor of 10. I think he got roughly 1 billion years, and the answer is more like 10 billion years, but that's just from measuring Hubble constant. Okay, so, all right. I believe so. It seems odd, doesn't it? As far as I know, yes. And as far as I know, he got it from the measurements, as far as I know. I don't know that he had any deep insight into it. All right, so now looking at this equation here and saying that this is negligible compared to this, 1 over a squared then is h squared, and h squared is 1 over the age of the universe squared, it's telling us something about the size of the universe. It's telling us the size of the universe is basically the age of the universe. Now, there is a speed of light in here. A is measured in length, t is measured in time, and so what this is telling you is that the size of the universe is essentially, the size of the universe is about equal to the distance light will travel in the age of the universe. No, this is not true. None of this is true. This is what was expected to be true on the basis of cosmology 40 years ago. These equations with dropping the various terms that were thought to be negligible. And as I said, one ingredient in this, several ingredients. First of all, radiation negligible. This is true. Matter being substantial, but still small. Only 1 proton per cubic meter, and only about 1/20th of this side here. And lambda being, as far as anybody knew, was 0, was thought to be 0. So that's what went into that. And that's why for all these years people thought that the radius of curvature of the universe was about equal to its age. Something that we no longer think is true. Okay. The first change had to do with dark matter. So let's just talk about dark matter a little bit, what it has to do with. I think probably most of you know the dark matter story, but let's spell it out anyway. Ordinary matter made out of electrically charged particles radiates. It radiates when it's accelerated. It radiates when you collide with it, and it's called luminous because it radiates. It's a kind of matter that we know about from direct telescopic observation, and it's what went into here. On the other hand, there's another kind of definition of matter, which is how much it gravitates. What's the mass of matter which gravitates? And of course, at first it was thought that the galaxies were made of luminous matter, and the mass of a galaxy was just the mass of its luminous matter. It goes way back. I didn't know how far back it went. It went back to 1932. I didn't know this. I thought it was a little bit later. 1932, the Dutch astronomer Oort, I'm not sure how you say his name, noticed that there were some things wrong with the way galaxies were behaving. A year later, Fritz Zwicky, who I did know about, noticed that clusters of galaxies were misbehaving. And by misbehaving, it meant that the gravitational behavior of them was inappropriate to Newton's laws, also Einstein's laws. Inappropriate to Newton's laws, and suggested that there simply was more matter out there than had been accounted for by this. So I'm going to take you through that. I think most of you know the story of dark matter. Yeah.
When you say luminous matter, do you include things like diffuse gas that might not be radiating?
Yeah.
But it could if it were under the right.
Yeah, and how you separate diffuse, almost everything radiates a little bit. Almost everything.
Black holes in the center of all the galaxies.
What's that?
The supermassive black holes, do they amount to very much? And
But-
would we count those as luminous matter?
Yeah, count them as luminous matter. Okay. Now, how, and of course, they're not luminous matter, they're black holes. But the point is, it doesn't matter whether we count them as luminous matter or not, because they're a small fraction. The galaxy at the center of black hole, no, I take that back. The black hole at the center of the galaxy is roughly about anywhere between 1 million and 1 billion solar masses. The galaxy is 10 billion, no, 100 billion solar masses. And so the black hole content is small. It's not a major, and that's not the, and besides, it certainly could not be the dark matter because it's concentrated at the center. Whatever the dark matter is, I presume it was Oort who first understood, it is not concentrated at the center of galaxies. So let's just go through the argument. The argument has to do with the so-called rotation curves of galaxies. You have a galaxy, and you look at stars at different radii, and you look at their tangential velocity v. All right. Let's begin by assuming something which would follow if all of the matter was luminous. The fact is that most of the luminous matter in the galaxy is in the center of the galaxy. By far, the majority or the overwhelming majority of the material is at the center of the galaxy, at the galactic center. And so for gravitational purposes, the outer things in the outer parts of the galaxy are moving under the influence of a central force, where the central force is just the mass near the center. Now this turns out to be wrong, but let's follow the logic of it for a minute. Let's use Newton's equations, F equals ma. The gravitational acceleration due to a mass at the center would be m times g divided by the radius squared to the star, and that has to equal the acceleration, and the acceleration is the velocity squared divided by the radius. Acceleration is v squared over r. So this would then say that the velocity falls off like 1 over r. This is somebody's law. Do you know whose law this is? This is Kepler's law. This is Kepler's planetary law. It's usually expressed in terms of the period rather than the velocity, but this is essentially Kepler's planetary law. One of the laws. Which one is it? The second law? Whatever it is. Right. Telling you how the velocity of planets varies as a function of the radius from the sun. Same law here. And in particular, it says that the velocity falls off like 1 over the square root of r. Velocity falls like 1 over the square root of r as you move away. That's not what was seen by Oort, and it's not what's seen by anybody since. What was seen is that the velocity is pretty much constant. Not the angular velocity, incidentally. It's not like this thing is rotating like a big giant pinwheel. Not the angular velocity, but the linear velocity. The linear velocity appears to be constant. All right, so how do you account for that? Well, the way Newton would have accounted for it, I think, is he would have said, look, there's just more mass out there. So instead of saying all the mass is at the center, let's say the mass is distributed, and let's introduce a function m of r. M of r is the amount of mass contained within a sphere out to radius r. A planet, not a planet, a star at distance r moves under the influence not of a constant mass at the center, but a varying mass which varies like m of r. And in that case, let's put back the equation. It's mg over r squared equals v squared over r. Let's multiply it by r, and now say that v is constant. If v is constant, oh, we put here now m of r, not just m, but m of r. V is constant, doesn't change with distance, and therefore we find that m of r must grow like r. Just multiply by r, think of v as a constant, m of r increases as you move away from the center. And so as you move out, this is not the mass density, incidentally. This is the total mass within a radius r, apparently increases linearly with r out to the outer boundaries of a galaxy, and even beyond that. We see things, you know, at the very, very far edges of galaxies, we do see a stray star here and there. And this can be, yeah.
So the luminous matter, you know, is much more dense in the center.
That's right.
But the non-luminous matter seems to sort of magically adjust for that so that the density, not the density, but the mass is a linear function of the radius.
Yeah.
Do we know, is there any theory as to why that would be? Because it seems very neat, very neat.
If there is a theory, I don't know it. But my guess is that by now people who simulate galaxy formation could probably tell you that this is not an unnatural thing. I definitely do not know a simple explanation for it. So at the moment it looks like a piece of luck that the velocity curve is just flat. And I don't know a good, substantial, simple argument about why that's the case. So, tell you what, I'll ask some of my colleagues if anybody knows. I know people who work on galaxy formation. But my guess is by now it's a combination of observational fact and simulation fact. Okay, so that's the status of galaxies. The other thing, incidentally, is we know that from the motion, even from the motion of stars perpendicular to the plane of the galaxies, that it looks as if this distribution of mass is spherical in character rather than conforming to the odd spiral or flattened shape of galaxies. Now, I can tell you for sure, I do not understand why galaxies have spiral arms or why they look like flattened disks. I looked it up more than once. I've looked it up in various places, and you get some very complicated explanations. It's apparently not simple. And it's certainly not that the galaxy is going around like a pinwheel. It is not doing that at all. So what do we know about this dark matter? Just from the fact that it seems to be more or less spherically distributed, and it seems to that the m of r grows as r out to distances that are almost midway between neighboring galaxies, one can estimate by now, I think rather accurately, how much dark matter there is. This dark matter is the non-luminous variety, and it is roughly a factor of somewhere between 5 and 10. And when I say it's a factor of 5 and 10, I mean to say that somebody knows whether it's a 5 or 10, but I don't. I always thought it was 10. I looked it up today, and it was more like 5. So let's say 7 times. But it's whatever it is, it's of order of magnitude 10 times larger than the luminous mass. Now, why doesn't it collapse? And it's bigger. It's bigger in size. If a galaxy looks like this, you know, it's a little pinwheel about that big, the halo around it is quite a bit bigger. why didn't it also fall together the same way that the luminous mass did? Well, the luminous mass fell together, meaning to say it collapsed in this form by losing energy. It lost energy to radiation, among other things. It lost energy to collisions. What kind of collisions? Collisions having to do with electromagnetic forces and things. And in the process of colliding, losing energy, radiating, it sort of fell into the center to some extent. So what we need to expect then about the dark matter is that whatever it is, it's much more weakly interacting. In particular, it's not electrically charged. Now, of course, if it were electrically charged, we would see it, it would radiate. So it's not electrically charged, but the fact that it's not electrically charged and that it is very likely rather weakly interacting, maybe like neutrinos, maybe a little stronger than that, means that these particles that make up this halo here, they circulate around, they may go back and forth this way, some of them are going this way, some of them are in elliptical orbits, but they don't interact with each other very much. And because they don't interact with each other very much, over the period of 10 billion years, this halo matter has not collapsed and followed the luminous matter. So the luminous matter, there's no question that to some degree they do follow each other. There are no, as far as I know, no large lumps of dark matter that don't have some kind of luminous matter at the center, and I don't believe there are any galaxies out there that are visible that don't have luminous matter around them. But it doesn't follow, they don't follow each other in the detail that the dark matter has a shape which looks like a galaxy. It just looks like a great big sphere, a halo. I think he was looking at clusters, yeah. Yeah. That's right, he was looking at the motion of galaxies in clusters. That's correct, that's correct. Oort was the one who looked at galaxies, and I understand he was first, but the scale, that's good, good. So that's right. So there is evidence for this kind of thing on multiple scales. It's not all coming from galaxies. It's coming from galaxies, it's coming from interaction between galaxies, and it's coming from whole galactic clusters. Yeah.
So when you say that that dark matter is weakly interacting, that
if it's made out of particles, which everybody believes it's made out of particles,
does it interact? Are the gravitational laws the same for dark matter?
We sure think so.
Okay.
Remember.
So in that sense, like two pieces of dark matter are going to be attracted with the same forces.
Mm-hmm.
So what do you mean by the fact that they're weakly interacting? No electrical forces?
Yeah, no electrical forces. No. Yeah, the emission of gravitational radiation by stars and other things moving in galactic orbits and so forth is completely negligible on the energy balance. So radiation of gravitational waves is not an efficient way for things to lose their energy.
Wouldn't dark matter tend to congregate around black holes because they do interact gravitationally?
And it does. And it does. It does. It's very likely that the dark matter, this was controversial for a while. I don't think it's controversial anymore. That the galaxies formed by first the dark matter collecting in these great big halos, and then the baryons, the protons, neutrons, electrons, and so forth, falling into the dark matter halos. That the dark matter, that the big things were there first, and then the smaller galaxies formed. They formed stars, and probably I don't know how early the black holes formed, and I don't know if anybody does, but the black holes may have been consequences of simply a lot of stars falling together. So it wasn't that the dark matter formed around the black holes. The black holes are a negligible amount of the mass at the center of galaxies. It's that the galaxies formed as a consequence of the halos of the dark matter. That's probably the way that it worked.
But wouldn't the density of dark matter be higher near a black hole because of gravity?
Yeah, it would be somewhat. Yes, it would certainly be somewhat. Yeah, I mean, we think that the density, for example, we think that the density of dark matter near the center of the galaxy is significantly higher than the density of dark matter away from the galactic center. And therefore, if people who are looking for example, radiation coming from the annihilation of dark matter, two dark matter particles colliding, annihilating, forming radiation, where would you look? You would look toward the center of the galaxy, for sure. So yes, it's more dense near the center of the galaxy.
Is there any way that we can know at what level dark matter is aggregated? Is it gas, or is it dust, or clouds?
It's probably just lonesome particles. We don't know, but it's probably just lonesome particles. What does dust mean? Dust means assemblages of large numbers of particles that hold themselves together by what? By electrostatic forces, by all the usual things that hold things together. If those kind of forces existed between those particles, they would not have survived as these kind of dark matter particles. So the expectation is that they are simply lonely particles that are lonely.
Through space through these particles.
What's that?
If the sun is moving through space through these particles, wouldn't they tend to be trapped in the solar well?
Well, yes. There's probably some abundance of them that is somewhat trapped near the sun. Yeah, but yeah.
If I combine these two, it says that velocity is independent of r. Is that correct? It's
Yeah.
velocity.
Velocity is independent of r.
So that says that the angular frequency goes like 1 over r.
Yeah.
So doesn't that explain that kind of spiral?
Go look up the spiral arms of galaxies and try to see if you can decipher the explanation. Some people think that they're shock waves of star formation, shock waves propagating around in circles and not moving with the galaxy, incidentally, not moving with the dark matter. There's other pictures, none of which I understand. Yeah.
Why would we think it's not one of the standard particles, like a neutrino or...
Neutrinos are very light, and because they would be so light, they would have to be pretty relativistic to have that much mass. And relativistic particles, okay, so one fact about these particles, which is most important, is that they cluster. That they tend to cluster, the gravitation makes them cluster. Things cluster less when they have high velocity. If these particles had high velocity, they would tend to cluster less. It's kind of obvious that if you have a gas of stuff and it has gravitational attractions, if it's hot, it will tend to resist the clustering tendency due to attractive forces. If it's cold, it will tend to cluster. Neutrinos, being so light, would tend to be pretty relativistic. They would be what is called hot dark matter. Hot dark matter is no longer an option. It's thought that the dark matter, basically because of this tendency to cluster, a strong tendency to cluster, is cold. Cold means to say that the particles are moving relative to the local reference frame with much less than the speed of light. So neutrinos are not a good option for dark matter. Yeah.
One thing I'm confused about in your explanation, you were saying, well, the matter in that equation up there with the four pieces, that the curvature piece dominates over the matter part. That's what they thought.
That's what they thought.
Yeah, but then at the same time you're saying in a matter-dominated world, A goes like T to the 2/3.
Oh, up until the time that this gets bigger than that. Right. You'd have to correct. All right. So the equation that what is it? That H is like 1 over T. That would get somewhat corrected, but not a lot, because most of it was happening earlier before this crossover point.
So, again, at the 30 or 40 years ago, what they were
And the point is, you can work it out. You can work out the detail. Yeah.
like 30 or 40 years ago, what was considered, what was dominant, what is time now? Is it matter dominated over the curvature, or is the curvature dominated over the matter now?
When now? Today?
Yeah,
You mean today according to yesterday's theory, or today according to today's theory?
the way they were thinking about it 30, 40 years ago.
Okay, so there was massive confusion. There was a lot of confusion about it, but I think if you would have put things together without worrying about dark matter, I think you would have had to say that this term was big, that it was of the sign that k was negative, and that a was roughly the same as the age of the universe. Yeah. Yeah. And people resisted it to some extent. The main reason I don't know what people were thinking. Each person was thinking something different. But I think one of the prejudices was that the universe was closed and bounded. So they would tend to write equations that were appropriate for k equals positive, and that conflicted with the observations. So there was a lot of confusion about it. Later on, 20 years ago, I'm not sure exactly when, it sort of settled down that k was probably negative. Okay. Now, what happened? Let's come now. What did dark matter do to this equation? Well, the left, if we just ignored this, the right side and the left side, the matter-dominated term over here, and the Hubble constant differed by a factor of 25 or something like that. So it was pretty serious, a big gap between these two. At best, the dark matter is 5 or 6 or 7 times the luminous matter, and it did not fix this. It fixed it somewhat, but it didn't fix it. It didn't make the matter term equal to the Hubble constant term. What it did was it still not only left room for a k over a squared with negative curvature, it required it. It required this term to still be there, so it didn't. Well, when I say it didn't fix things, I'm not sure what fix means. There was nothing particularly wrong with saying that h squared largely came from here, but the matter term was not sufficient to fill the gap. It still had this present.
Are there any sort of restrictions on the mass of the particles with dark matter?
No, essentially none.
If you got too light, would you have a problem that
Yeah. It depends. All right, if the particles are light and fermions, you're in trouble. They can't all occupy the same state and be moving together slowly relative to each other. If they're bosons, they can be extremely light and be in a phase called a Bose condensation. And the Bose condensation just has very, very slow particles, all in the same quantum state, moving like a Bose-Einstein condensation. And that is one of the theories of dark matter. It's called the axion theory, that the axions are incredibly light, very, very light. I don't remember the exact numbers, but extremely light, much, much lighter than neutrinos, and that they form a Bose condensation. That's one theory of dark matter, and it's a good theory. It's not a crazy theory, but mostly people think about theories in which the dark matter are particles that could be detected in big accelerators, particles whose mass are in the range of masses that could be discovered at at the LHC. Is that because, is that wishful thinking? Well, yeah.
They can't get enough power yet, right?
They
to
can't get what?
close. They don't have enough power yet in the accelerator to try and reach the theoretical maximum that they're looking
No,
for.
no, there is no theoretical maximum unless you assume that the particles interact with roughly standard model weak interaction cross-sections. Then the maximum is probably up in a few TeV, a few, maybe at most 10 times 10 TeV. And yeah, I mean, is there enough energy to have detected them? Apparently not.
Well, in 2 years we'll be adding more, right?
And the 2 years will have more information, and it is possible that particles will be discovered, and they may have the right properties.
So would it be fair to say that the dark matter, could we blame string theory on it and say
No.
that the reason
No.
that we can't see it is
No.
because it's
No,
saying
no.
a dimension that we can't see from our own?
No, 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 no. I mean, they are particles. They can be seen. They can be measured. We do measure them. We measure them gravitationally. I guess you're asking, is it conceivable that these are particles which are so unusual that they have almost no interaction with ordinary material, and therefore we don't see them? Yes, it's possible.
And that's why we struggle.
But yeah, that's right. But it is possible that they are just so weakly interacting with ordinary matter that that there's no chance of detecting them. It's possible.
One of the reasons that neutrinos are so fast is because during the Big Bang they were formed at a, so if this dark matter was formed at the Big Bang, would it have been formed later when the universe was cooler or something?
No, no, no. They're just heavier.
Oh, I mean, if they were light.
If they were very, very light, okay. Yeah. If they're bosons, it's okay. They can boson condense, and they don't have to be moving fast. If they're fermions, they have to be moving fast. Okay, the axion theory is not a theory in which the axions were ever in thermal equilibrium. If they were in thermal equilibrium at one time, then they would be moving fast today. But this is not where I was going with tonight's lecture. I wasn't going to get into axions. We know with any confidence nothing about dark matter. The most likely thing is it's some form of elementary particle that hasn't been discovered yet. A good chance that they're heavy enough to have escaped detection in the LHC, but light enough to be able to be detected in future experiments. But that's it. That's about all we can say at the moment. And they're there. The other alternative to dark matter was to modify gravitational theory so that Kepler's laws doesn't work for galaxies. But that doesn't seem to have worked very well. There don't seem to be any nice modifications of standard gravity theory which explain this. So most of us think it's particles, but you're free to make other theories.
Hasn't necessitated any modifications to the Newtonian mechanics by which we understand our own solar system.
It has not.
So by that, we can conclude that there's a negligible amount of dark matter around us.
That's right. That's right. Yeah, keep in mind, the density of matter in the solar system is a lot higher than it is out in, the dark matter in the solar system does not compete with the gravity of the sun at the center, not by a long shot, and so that's right. It doesn't affect the solar system. Okay. All right, so it's natural then to ask, can we make how do we test the candidate theory? Here's the candidate theory now. The candidate theory is matter dominated. We forget this. We forget lambda because that's something we hadn't heard about. K here is negative and negative curved space. How do we test that theory? Okay. How do we test any particular model? A model, incidentally, consists of two things. It consists of a specification of K, whether it's 0, +1, or -1, and some kind of equation of state for which you could substitute a history, an A of t. An A of t and a K is a model that you can try to test. So what do we know, and what can astronomers measure, and how do they compare it with a particular model? Well, pretty much the same thing Hubble did, except a sophisticated version of it. You can measure two things to a large extent. You can measure the redshift of things, which tells you something about their velocity, and you can measure distance by luminosity. How do those two things come together to tell you anything about K and A of t? So let's talk about that a little bit. First, let's ignore the fact that h, the Hubble constant, changes with time. And let's just suppose we didn't have to worry about the fact that the universe evolves. Let's just suppose for a minute that it was all at an instant and that it didn't change. What could you do to measure K? Whether the universe is open or closed or what? And the way to do that is to measure the number of galaxies out there of a given brightness. What does the brightness have to do with K? So let's talk about that. If the number of galaxies as a function of distance, really, that's what you want to do. You want to measure the number of galaxies as a function of distance. If you happen to think that distance is related to redshift, which of course it is, then you could be talking about the number of galaxies as a function of redshift, but let's just talk about the number of galaxies as a function of distance, where the distance has been measured in some way that we need to come back to. All right, so if we're living in a flat space, then it's clear, and space is homogeneous, and everything is homogeneous, then it's pretty clear that the number of galaxies in a region dr, let's say within a shell surrounding us, the distance dr goes like r squared. That's just the volume of a r squared dr. It's also true that if we lived in negative curved space, it would go like hyperbolic sine squared of r, and that means something which grows exponentially with r, e to the 2r dr. If we were on a sphere, if we were living, not this sphere, but if space was a sphere, this would become sine of r squared dr. But let's forget that. The evidence seems to say negative curvature. This is the case for negative curvature. And so the first thing you can see is the number of galaxies as a function of distance would grow much, much more rapidly as a function of distance. What about as a function of luminosity? What can we say as a function of luminosity? How does the luminosity, in particular, another question you could ask is, how does luminosity depend on distance? Well, how does luminosity depend on distance in flat space? What's that? It goes like 1 over r squared. Right? It's just the same fact here. If you thought of a light bulb at the center and us out here, then the luminosity of the light bulb, the amount of radiation coming out, would simply be spread over the area of the sphere here, and the area grows like r squared. So the luminosity itself goes like r squared. But supposing you were living in this negatively curved space where the area of the sphere grows like e to the 2r, then the luminosity would be much smaller. So what you would find would be a very rapid fall off of luminosity with distance. You would find many more galaxies out there at a given distance, but you would find the luminosity as a function of distance would fall off much faster. So in particular, you could ask, what about luminosity as a function of redshift? And you would find a characteristic behavior of the luminosity as a function of the redshift, which would say the luminosity really gets small fast because of this e to the 2r here. So that would be, that's pretty much the way of determining whether k is +1, -1, or 0. That in particular, if k is -1, meaning to say negative curvature, one should find that the number of galaxies at a given distance, or let's say at a given redshift, anomalously grows rapidly with redshift. Okay? As the redshift gets deeper and deeper into the red, number of galaxies should grow much faster than it would in flat space. So that's a test. You can also think about calculating the number of galaxies that you see as a function of redshift. How many galaxies do you see as a function of redshift? Forget the dimness and the brightness for a minute now. Just how many galaxies do you see at each redshift? That's something you can also calculate. Let's talk about it a little bit, how you do that. Well, in order to talk about it, we have to talk about redshift. What is redshift? All right. If light is emitted by a source that has a wavelength lambda, we can call that the wavelength of the light when it's emitted. Emitted, just the usual. If it's a light bulb, it has a certain wavelength. Right? When it's detected, the light may or may not have the same wavelength. There could be various reasons for a shift of the wavelength. Doppler shift is one. Gravitational redshift from gravity due to a black hole is another one. And the expansion of the universe, which happens to be equivalent to the Doppler shift, is not a third, it's equivalent to the Doppler shift. But the expansion of the universe is the one that we're interested in. So here is what is going on. Let's draw a map of the universe. This is time, horizontal is space, and here's today. We're right at the center. This is r equals 0. And different r correspond to different vertical lines here. This is r equals 1, r equals 2, r equals 3, and so forth. All right. We look back, and we look back along light rays. So how do light rays move? Well, in flat space, in the Minkowski metric, they move on 45-degree lines. But this is general relativity. There's a complicated metric here. We'll discuss a little later how light rays move. But however they move somehow. Either straight lines or curved trajectories. Well, somehow light rays, we'll figure that out later. But we look back, and we see a galaxy over here. We see a galaxy over here. We see a galaxy over here. And we see a galaxy over here. We see them at different times. And because we see them at different times, we see them first of all, with different scale factors. The scale factor varies vertically here. There's an A of t. Up here, there's A today. Let's call that A today. The emission point over here, let's just call A of t. The light emitted over here has to stretch to get to here. The universe increases by a factor of A today over A at the emission time. A today can just be thought of as a number. A at the emission time depends on the emission time. Okay. That's the factor by which the wavelength of an electromagnetic wave will stretch, and going from here to here. And that's, in fact, the redshift factor. We should define redshift carefully. Let's define redshift carefully. It is the ratio of lambda when it's detected divided by lambda emitted. And that's not quite right. Is it -1 or +1 times that? -1. -1. Why is the -1 there? For historical reasons. And it's called Z. Z is the redshift. Okay. And lambda detected over lambda emitted is just the ratio of A today over A of t. Okay. So we look back along a light ray. We see light emitted over here. We see light emitted over here. We see light emitted over here. And each emission has a different redshift factor. The redshift factor, this -1 is equal to Z? A today, yeah, this -1 is equal to Z. All right. So if we know the scale factor at the time of emission, then we know what Z is. Okay, so that's good. But so far we don't know anything because we don't know how the light ray moves. Until we know how the light ray moves, we don't know how to compare these points. So let's talk about how the light ray moves. Let's work out all the things we need, and then I'll write down some equations for you which an astronomer would actually work with. Okay, so what's the next thing? How does the light ray move? We go back to the metric. Here's the metric over here. And light rays are null rays. Light rays, in particular, light rays that are moving radially relative to us, here we are over here, light rays moving radially to us are null rays, which means that dt squared is equal to A of t squared times dr squared. All right, so we can write then for a null ray, for a light ray moving backward like that, an imaginary backward moving light ray, that dt is equal to A of t dr. Now this is, I don't quite have it right here. I have the sign wrong. Of course, what's true is dt squared is equal to A of t squared times dr squared. Now there are two solutions. One for going back into the past, and one is going forward in time. Obviously the one we're interested in is the one which goes back into the past, and for that, dt is equal to minus A over t dr. All this says is that r gets bigger as t gets more negative. As t gets more negative, r gets bigger. All right, so there's this funny minus sign there. It's a peculiar minus sign. Or the dr is equal to dt over A of t with a minus sign. All right, so this is one equation, and that tells us how light moves. That tells us how light moves along here. And let's now see if we can invent an equation, invent a question that an astronomer would be interested in. Here's the question. What is the number of visible galaxies of a given redshift? Just that. What is the number of, let's call it dn, the number of galaxies within redshift z and z plus dz? The number of visible galaxies per unit redshift. That's something that surely can be measured. Look out, you see the galaxies, or if they're galaxies or whatever the standard candles are, and you count the number at each redshift. Okay? That'll give you dn dz. Let's see if we can figure out an equation for it. What about dn? What about dn? dn, let's just take that to be the number of galaxies within a sphere of radius r and differential distance dr. What's that going to be? It's going to be equal to the area of the sphere times dr. So dn is going to be dr. And what's the area of the sphere? Nope, not in general. Not in general. That would be correct in flat space. In general, it's proportional to xi of r squared. In other words, in the case of interest, where k is negative, this would be hyperbolic sine of r, and at large distances it would be some exponential. But of course we can study all of the cases. We can study all of the cases simultaneously by putting psi of r squared. Times what? Times a number which is the number of galaxies per unit volume, but let's leave that out. Let's just write proportional to. The number of galaxies within a shell is proportional to dr times xi of r squared. Now what about dz? Let's look at z. Here's z, and we're interested in the change in z from going from one radial point to another radial point at distance dr. How much does z change? Well, let's just take this equation here and differentiate it. dz is equal, the derivative of -1 is 0. A today, what's varying incidentally? Is A today varying? No, A today isn't varying. A today is just A today. What's varying as you look back along here is A at the emission point, A of t. So that's equal to A today. And I want to differentiate 1 over A, so that's minus A of t squared. Derivative of 1 over A is 1 over A of t squared times dA, right? dA of t. Everybody recognize that equation? So we have to divide by dz. That's minus A today over A squared dA. What is dA? dA is dA by dt times dt. I haven't done anything. I've just manipulated the equation a little bit. What is dt? dt is it's not quite. No, it's not quite dr. It's not quite dr. That's what. No, we have dr by dt. What's dr by dt? Here it is. dr by dt is minus 1 over A of t. Right? Along a light ray. That's why I had to do this. That's why I had to figure out what that is. So dA, let's see, so let's put dr by dt. And dr by dt is minus 1 over A, so that gets rid of the minus sign and gives us another A downstairs. Good. The A's cancel. This A cancels this A. I don't like it. It's not what I have in my notes. Yes, it is. What's A today over A? Z plus 1. Okay, so A today over A is Z plus 1. Okay, so here I have the number of galaxies seen at redshift Z contains a factor 1 over Z plus 1. Okay, that's known if we know Z. And then it has C of R divided by A dot. What can we do with that? Let's see what we can do with it. There's nothing we can do with it now. There's nothing we can do with it until we make a model. Until we make a model. So let's make a model. Let's make a model and see what we get. Do we really want to do this now? Yeah, let's do it. All right, let's make a model. Our model is the matter-dominated universe. Let's take the matter-dominated universe with k equals minus 1. And for the matter-dominated universe, for most of the evolution, again, A looks like t to the 1 to the 2/3. Here's what we want to do. I'm not going to go through the whole story. We can calculate A dot. A dot is equal to 2/3 divided by 1 over t to the 1/3. We calculate A dot. What about R? Can we calculate R? Yes, we can calculate R. Once we know A of t, we can calculate R. I won't do the calculation, but we also know R of t. It's known. We can compute it. Moreover, once we know A, we can calculate Z. The point is that everything, A dot, R, can all be expressed in terms of Z. We know that, and A today. We know the relationship between A and Z. We know the relation between A and T. In other words, we can write everything in terms of Z. Everything here is known in terms of Z. And so we get a thing here which depends on Z, but it's known only because we substituted a particular model. Had I used a different equation of state, I would get a different answer. C of R, that's an interesting quantity. That exponentially increases with R. That's easy to detect. That's really easy to detect, that C of R, this explosive thing which is just increases with R. That means since R increases with redshift, that makes an anomalously large number of galaxies at large redshift if k is negative. And A dot can be computed directly in terms of Z. In other words, the point is, with enough little bit of labor, you can take a model, which means an A and a K, and convert it into a statement of how many galaxies you see per unit redshift, together with the other piece of information, which was the relationship between redshift and luminosity. Those two bits of information together can give you a complete history of the expansion of the universe. That's enough to give you a complete description of the expansion of the universe and to tell you what C of R is. I've assumed something about C of R, but I didn't have to. I could have done this calculation in flat space. I could have done it in a closed universe. The two pieces of information are redshift not redshift, luminosity as a function of redshift, and the number of galaxies as a function of redshift. Those two things together are enough to determine A of t and k, whether it's +1 or -1 or 0. All right, so you do that. Astronomers do that. They've been doing it for 50 years or more. And the final upshot is, first of all, inconsistent with this matter-dominated universe with k being negative. What it's consistent with, the best fit from, incidentally, when I say galaxies, I mean standard candles of some kind. And the standard candles which are best at the redshift we're interested in are supernova. Supernova are things which are very controllable. We can't control them, but we can, nature controls them. And the result is not this formula at all, but omega radiation, again, essentially equal to 0. Omega matter, and this includes both dark matter and luminous matter. Dark matter and luminous matter about 0.3. Omega lambda about 0.7. And omega k about 0. This is observational fact. Very little theory has gone into this. Well, theory has gone into it, but no particular biases about what to expect. This is pretty much what the unbiased raw data says. And 0, he means it could be 0.1 or it could be minus 0.1. But no, I take that back. Whoa, 0.01. Could be 0.01, plus or minus. It could be that small, or it could be that big. Omega lambda is about 0.7, omega matter about 0.3. That's the best fit to these various pieces of information here, using models which depend on the equation of state. Okay. So just from counting galaxies, redshift and luminosity, that's the picture that emerges.
I thought lambda wasn't even known yet.
No, I'm talking about today. Now I'm talking about today. This model, this theory failed. It failed. It failed this test. It just could not reproduce the observed luminosity Z relation and dN dz. It just failed.
So, but is the way we know omega lambda is from the equation? We're not measuring
Yeah.
omega lambda, are we?
No, you put in, yeah. You put in numbers for these things. The model consists of numbers for these things. That's what goes into the model. A value of omega k, a value of omega lambda, and a value of omega matter. Or equivalently, C matter, radiation is not important, lambda and k.
I guess my question is, from what you're talking about, taking these measurements, just taking measurements, you said we could kind of figure out what k had to be, or what omega k and omega m had to be. Is that right?
You have to process it through this.
Right.
Yeah. You have to, this is what you begin with. No, you don't begin with this. You begin with a value of omega k, a value of omega lambda, a value of omega m, and a value of omega r.
Just to get sort of a guess? Is that what
No, you start with a number. You start with a set of numbers. That defines a model. Now you process it. Now you run it through the equations. You run it through the mill, and what you calculate is L of z and dN by dz. You compare them with experiment. If it fails, you throw the model away and put in some new numbers. And you keep trying numbers.
What you're saying is that one works.
That one works. That one works with some uncertainties, but the uncertainties are not big. This one is rather small, 0.01. They're all small. They're all in, I think this is 0.28 if I remember, 2.8 and whatever. Let's call it 0.3. So they're known to about 1%. These numbers are known to about 1%. And if you vary them very much more than 1%, these tests fail. Okay. So a model then, again, a model consists of a specification of these values, which means the values of the various components here today. But you don't measure them completely. Some of them you measure, some you don't measure, but you just feed them in, grind the wheels, calculate A of t from the Friedman equation, calculate A of t. Once you have A of t, you can feed it into here, calculate the n by dz, and luminosity is a function of z, and test it. Yeah.
Just to remind us, is A today, where does that comes from, the Hubble constant?
Yes. Well, once you have a model, you're juggling various things, but once you have a model that fits these two pieces of data, okay, then you have an A as a function of time, and you can read off it what A today is. Yeah. And it's roughly speaking from the Hubble constant today. Yes, it's from the Hubble constant today. So that is one of the outputs. One of the outputs is A today. And
earlier you said that, I think you said something along the lines of you doing this looking not that far back into time. If you were to have gathered this data by looking very far back in time, wouldn't that distort it because you'd be, I mean, maybe it's the same point, because you'd be looking back at it.
you know, if you only took your data from very, very far in the past, the only term that's important here is this one. If you go to very small a, which means long in the past, this is simply much bigger than this and this.
But if you're not going that far, I mean, let's say you look back 1 billion years, 2 billion.
Oh, 1 billion years is not very far.
That's not enough to distort the answers that you got from this.
What do you mean to distort it? That's what you do. You go back 1 billion years, 2 billion years, 3 billion years, 4 billion years, and that's what goes into these equations. A of t. A of t as a function of t all the ways back up to the present. Yeah. All right, let's go back through it again. You begin with a set of values of the matter density, the cosmological constant density, all of these. They go into the Friedman equation.
I know you answered was before. Where did we come from? These numbers?
No. You just invent them.
No, but really, I mean, it's
Did the ratios over that over the Hubble
Where did you get
constant?
those values? Where did you get those values?
We start with some other values. We feed them into here. We calculate the n by dz. That's an observable thing. The number of galaxies, how the number of galaxies varies with z. We observe it. We calculate L of z. That's also an observable thing. If the model doesn't work, we throw it away and try some new numbers.
Right. No, I understood all that. Where did you get those?
I didn't get them.
No, but how
Trial and error.
How did you ever got them?
Trial and error.
It fits the data the best.
You have a machine that starts with a set of 4 numbers. This one is not important. Everybody knows that this is not important because you measure it directly. It's just too small to matter.
So you
Okay.
put these in Friedman's equation, that allows you to compute d and dz and L of z, and
Yeah.
these numbers give you a good fit.
Yeah, these numbers give you the best fit. Right.
Well, this is what you do with spreadsheets all the time.
Yeah. All right. Some of them, look, this one here is more or less measurable directly. Why? You can measure H is measurable, and you can measure the dark matter and the luminous matter together, and basically omega m is the ratio of this factor over here, this one to this one. You measure the energy density in matter, you measure the Hubble constant, and the ratio of them is omega m. So that actually is measurable. It's really this one here, which was the unknown. So, all right, so what can you say? This one is pretty much directly measurable, omega matter, and it's 0.3. With an assumption about dark matter. Yeah, including the dark matter, omega m is about 0.3. These two are the ones which are not known, but what is known, at least in theory, is that this plus this plus this has to equal 1. Right? This plus this has to equal 1. This one is known, therefore this one follows. But you want to do better than that. Really what you want to do is, you really want to do better than that. You just don't want to say, well, this was 0.3. This one's not really known. Nobody's ever measured the curvature. And therefore, this one must be 0.7. That's not what you want to do. You want to take, this is given, this is unknown, and omega k, whatever it is, to fill up the difference. Okay. You with me? You take this one as known, this one is unknown, but we'll put it in as a trial, and omega k is just what's left over. We put that into these equations, we run it, and we calculate L of z and dn by dz. Having done that, we just look for the best fit. I think I probably didn't say this clearly, so let me just try it once more. These two, this one and this one, are measurable. This is negligible, this is 0.3. These two are unknown, but what's known is that the sum of all of them should add up to 1. All right? So we take a test value for omega lambda. That tells us what lambda is. We run it through the Friedman equations, find out what A of t is. Having computed A of t, we go to this blackboard over here and compute the observable signature, the number of galaxies per unit z, and the relationship between z and luminosity. The relation between z and luminosity is a generalization of Hubble's original calculation. Luminosity is distance, z is velocity. The only reason we have to do better is because we're looking at it at different times. All right? So the additional ingredient is to have these curves, knowing how light moves and so forth. That involves the model. That involves the details of the model. But once you put the details of the model in, you look for your best fit. And the best fit is with these numbers here.
So the last two you treat as adjustable parameters?
Last two you treat, well, only one of them because they have to sum to, yeah.
That's sort of a question. Why just one of them? I mean, both of them appear in the equation. So why couldn't you guess lambda equals 0.4 and k equals 0.3 or something like that?
No, they have to add up to 1. These are.
No, they would add up. All that would add up to 1. Instead of 0.7, lambda equals 0.7.
Yeah.
And k equals essentially 0.
Yes.
Why not lambda equal 0.4?
Mm-hmm.
And then k equals 0.3.
Good. Good. You take this. You take your trial. You solve the Friedman equations with it. That tells you what A of t is for your model. You then feed it into here. This is not what you get. You get something different. Feed it into here and calculate the number of galaxies per redshift, or the number of supernova per redshift, and the luminosity as a function of z.
The only thing I'm pointing out is that's different than what you said. You said just take lambda, forget k, and let it fall out. I'm not even sure what that means. You were saying we only have one parameter, lambda, that we have to deal with, but I don't understand why.
Because this plus this plus this has to be 1.
Right, but as I said, if you just fix, okay, so you
Can we take it offline?
all right, I don't want to waste time.
No.
But
Yeah.
the point is that if you set lambda, you're forced to set a certain
K.
omega k.
Okay. Right.
Okay,
Right.
yeah, I see what you're saying.
Right.
I agree. Yeah.
Right.
I've got a question about K. You've been saying +1, -1, 0. Is it really K is greater than 0? Well,
No, the way we formulated it is +1, -1, or 0. But omega, yeah.
I'm having trouble seeing how the dimensions work there in K over K over A squared has to have the same dimensions as H squared.
That's right. The speed of light is equal to 1. Apart from the speed of light, that's correct.
Oh, I see. So there,
Yeah.
there's a C in it.
There's some
squared
C's in
in
there.
it.
There are some C's in there, yeah. Yeah, there are some speeds of light. But, you know, get used to working with speed of light equal to 1, and then this is dimensionally correct. Okay.
Does this method rely on the assumption that the density of galaxies is isotropic over space and time?
No, what does it mean for it to be isotropic over space and time? What does it mean?
Meaning that earlier in the universe, there might have
Oh,
been
that
more galaxies, but smaller ones per unit of...
it assumes that at every time space is homogeneous and isotropic. It does assume that. But, you know, that's to a large extent tested, not completely, but if you want to know whether it's isotropic at this time over here, you just look at galaxies that you can see at that time, and you see that it's isotropic. You look in different directions at different redshift, at the redshift you're interested in, and it's isotropic.
These omegas are the way it is today, but
Yeah.
in the past it would be different. So like in the early days...
The omegas are defined to be the ratios. Okay, so you have these four numbers, CR over a to the fourth, plus Cm over a cubed, plus lambda minus k over a squared equals h squared. That's true at all times, okay? Now we plug in today. Now we plug in today. Okay. Now we just take the ratios, divide it. Yeah, we just.
I understand that, but I mean,
Yeah.
like a zillion years ago, the omegas will be different.
A zillion years ago, the omegas would be different.
So my question is does the derivative of the omegas, in reference to time, what do they look like? Obviously, the wave one.
No. Here they are. Here you can see that long in the past, radiation was much more important than matter. Was much, much more important than lambda. So long in the past, a long, long time ago, omega radiation was large. Large means essentially equal to 1. Long in the past, omega radiation was about all there was, and everything else was small.
Right, so therefore d omega r is negative. The derivative of that, you know,
Yes,
omega r dot is negative.
Omega r is decreasing.
Right, and omega matter and the other one, what are they doing? Are they increasing or probably omega is probably 0? Derivative of it, I mean.
Yeah, omega, okay, so let's, when A gets large, what is going to be biggest here? Lambda is going to be biggest, right? So long in the future, omega lambda will be 1. Yeah, omega lambda will be 1, and everything else will be small. Omega curvature will be less small than omega matter, which will be less small than omega radiation. But long in the future, it'll be dominated by lambda. Long in the past, it was dominated by radiation.
Okay. So the real question is, what is the time derivative of matter look like? It obviously starts small, then it gets larger, then it gets small again.
Yes, that's correct. That's correct. The omega matter starts small. Why? Because it's almost all omega radiation. Right? Then it gets bigger. It starts to dominate. It gets up near, pretty big, up near close to 1. That's before lambda became important. And then lambda becomes more important than this. That's today. So omega matter is 0.3, and omega lambda is 0.7. And omega k. Is, well, we don't know that. We don't know that. Let's see. Yeah, no, right. It's not. No, that's correct. It's not going to. When I said we don't know that, I mean to say that we know that it's 0 to within about 1%. The next round of experiments might discover that it's not 0, that it might be 1%, either plus or minus. That won't change much. No. Well, let's see. Yeah, it will change. Sure, it will get smaller. It will get smaller. It will get smaller because this will eventually defeat this by any arbitrary amount. So yeah, this one will get smaller, and eventually all it'll be will be lambda. That's as far as we can tell. I mean, there's some theory that goes into that, of course.
When you put the values in, fit the data, is there any kind of systematic deviation that's not understood?
I don't think so. No. No.
So it's a good model.
Yeah. No. This has achieved the level of precision cosmology where everything does fit. Now, the only thing is, it's a 1% model. It's not a 1/10%, and it's not the 100%. It's a 1% fit, and everything fits to 1%. Yeah.
Independent of this, have they been trying to do experiments where they determine whether K is positive, negative, or 0 by trying to do huge triangulations and looking at angles to see if they're, sum up to 180?
That's correct. That's correct. And we're going to come to that when we study next week the microwave background. And the microwave background, or at least the lumpiness of the microwave background, allows triangulation and allows you to study triangles. And again, probably if all you use is the supernova data, this is the supernova data, I don't think that gets you to 1%. Maybe it gets you somewhere between 10% and 1%. Combined and supplemented with a cosmic microwave background, it's 1%. Yeah.
K to 0, then it says the universe is becoming flatter.
Becoming
flatter.
Yes. Oh yes, for sure. For sure. Sure, the bigger it gets, the flatter it gets. That's just big is flat. In any case, if it continues to grow, it will become flatter. Okay, this is tricky stuff, but the way to think about it is what I said. You start with a model, which means a set of parameters here. You feed them into Friedman equations. You go to this side once you have Friedman equations, and you can read off from the Friedman equations the observable quantities L of z and dn by dz. And you compare. And there's incidentally no reason why any particular set of numbers has to agree with the data, other than theory. Without a theory, there'd be no particular reason why any set of numbers would agree with the data. So it's not just testing a particular model, it's testing a particular model and it's testing the theory. Yeah. Yeah.
For more, please visit us at stanford.edu.